All right, we're going to continue talking about logs today, and we're going to start on page 329. Yesterday was kind of our intro to logs, kind of how they operate or what they represent. If I were to start the sentence, logs are, how would you finish it? Or a log is what? Hopefully we didn't lose it from yesterday. If someone asked you what a log was, what would you say to them? Did we lose it? We're looking back. Maddie, can you do me a favor and shut that door? What's a log? In general. Yeah. A logarithm. Okay, so you can write a logarithmic equation. We can do log, for instance, log base 2 of 8 would be 3. Okay? But if this log is 3, what does the answer of a log represent? A log is what? Yeah.
The power of which the base is raised
to equal the argument. In short, a logarithm is a power. Okay. Specifically, the power you have to raise the base to get the argument. So you could develop a logarithmic equation, like Ashlyn said. Okay, but logs are powers. Keep that in mind. Anything for the office this morning? I think we're good. Thank you. You're welcome. Have a good day. Okay, so we're going to continue talking about logs today, but we're going to take a look at what's called a natural log or a natural base. Maybe you've seen these before or seen this before in some type of science class, but we're going to kind of develop this letter E. We'll talk about that in a second. So we're going to take a look at this expression, 1 plus 1 over n, all raised to the n power, and we're just going to plug in some values for n into that expression, and we're going to see what happens as the numbers get larger and larger and larger. So this is where I need you to use your calculator. If you were to plug in 1 for the n's, we'd have 1 plus 1, which is 2, and then 2 to the first power would just be 2. But they're going to get a little bit trickier when you start to plug in higher values for n. So let's check out 10. We would need to do 1 plus 1 over 10, close the parenthesis, and raise that to the 10th power. So go ahead and just write down maybe 3 decimal places if you want to round it on your paper. So 2.594. Alright, I want you to keep going through it, making the value of n get larger and larger and larger. Bless you. Maybe you'll start to see a pattern after a while. Alright, so taking a look at the table, as you let the n values get larger and larger and larger, okay, getting towards closer to infinity, what did you notice the value of the expression approaching or getting closer to? Yeah. Closer to 3, but notice how it kind of leveled off at 2.718. Do you think if I were to make this, like add one more 0 on the end, it would reach 3? Or do you think it would be another 2.718? 2.718, okay. So it's getting closer and closer to 2.718. There's more decimals afterwards, okay, but we're just rounding it to 3. This number is called E, okay, the letter E. You know how pi is 3.1415 ... forever? Okay? The letter E is 2.718 ... forever. So E is actually another irrational number. You cannot represent it as a fraction, just like pi is irrational. So you're used to the number pi, now we're kind of adding this new number where it's called E, and it's referred to as the natural base. So yesterday we talked about common logs. Okay, what was the base of a common log? If you don't see the little subscript, what's it understood to be? Yeah, 10. Okay, so common logs have a base 10. What we're going to talk about today is something called a natural log, and a natural log has this base of E. It's called a natural base because this number, 2.718 ... shows up quite frequently in nature, okay, or biology applications. So that's why it's called a natural base, okay? It's some type of natural phenomena in our world. So whenever you see the letter E, we're talking about a natural log. Now here's the thing. Based off of how we wrote logs yesterday, you would think that we would write log base E of A, okay, if this is the base we wanted to use. But that's not exactly what happens. We have something called the natural log, or ln in this case. Maybe you've heard of the mathematician, I think his name was Leonhard Euler. Euler is spelled E-U-L-E-R. He's the one that actually discovered this pattern, and that's why we use the letter E to signify his last name. Okay, he was a Swiss mathematician way back when, and the reason that this is called a natural log is because, I guess, in the French language, however they pronounced it, it was logarithmic or logarithm naturel. That's why it's ln instead of nl for natural log. So whenever we're dealing with a base of E, we're going to use ln. Do you notice how on your calculator there is an ln button? Okay, it's right underneath the log button we were using yesterday. So we have two different types of logs. We have the common log, which is a base 10, or we have the natural log, which is the base of E, this 2.718 number. Now a natural log is still a log, okay, it's just a special type of log because it always has this base. So since it's still a log, it has the same properties of logs that we were kind of discussing yesterday. So we're going to take a look at this change of base formula from yesterday and see how it relates to maybe a natural log change of base. So let's think about this. If we were to try to calculate the value of this log in our head, what power would you have to raise 3 to get 20? If it's not a nice whole number, maybe we can think about what it should be between. Yeah. Between 2 and 3. Okay, so 3 squared is 9. 3 cubed is 27. 20 is definitely between 9 and 27, so we should be anticipating a number between 2 and 3. So yesterday on our calculators, we said we had to convert this log base 3 into common logs. That way we can type on our calculator. So we would need log of the argument, which was 20, over log of the base, which was 3. All right, so if you were to type that on your calculator, log of 20 divided by log of 3, we get 2.727. Okay, but maybe instead of converting the log base 3 into common logs so we can use our calculator, maybe we can convert the log base 3 into a natural log, because we have that button on our calculator as well. It works the same way. Maybe we want to do natural log of 20 over natural log of 3. So we'll hit the ln button, which is right underneath the log button from before. And notice how we get the same answer. So a natural log is still a log, it just has a base of e instead of a base of 10 like that common log has. Okay, so e is 2.718. It's a special number just like pi is a special number. Let's go ahead and try the next one. Can you think of the power you have to raise 2 to get 1 over 16? Yeah. -4. We should be able to do that one in our heads, okay, because 2 to the 4th is 16, but since it's in the bottom of a fraction, it was flipped, signifying the power was negative. Let's go ahead and just double check that on our calculator. Maybe we're not sure of that answer from our head. So we do log of 1/16, or 1/16 over log of 2. Or you could type in natural log of 1/16 over natural log of 2. Do you get -4 in either case when you check your calculator? All right, let's try the last one. What power do you have to raise 5 to get 15? If it's not a nice power, what should it be between? Yeah.
Number between 1 and 2.
1 and 2. Okay, so 5 to the first is 5. 5 squared is 25. 15 is definitely in between 5 and 25, so we should get a number between 1 and 2. Again, on your calculator, you have options. You can either change the base of 5 to a base of 10 using the common logs, or you could change the base of 5 to a base of e to use the natural logs. Either way, you should get the same answer. Something between 1 and 2 for this case. What did you get? Yeah? 683. Okay, so just like yesterday, we said that we had a way of converting a logarithm. If it was a log base b of a, we can convert that to a common log. Okay, log of a over log of b. But now that we've kind of introduced this idea of a natural log, maybe you want to use that button on your calculator instead. Okay, they'll all give you the same result. Just depends on which one you're more comfortable with using. Okay, so common log is a base of 10, natural log is a base of e, and let's remember e is 2.718. Okay, that specific number. So what we're going to try to transition to now that we're getting kind of familiar with logs, is solving equations with logs in them. Okay, trying to solve for a particular variable. So let's go ahead and try, flip to the back and we'll check out these log equations. So at the very beginning of yesterday, we were practicing converting log equations into exponentials. That might not be a bad idea to help us maybe solve some of these log equations. So if you were to take a look at the first one, how could you rewrite the 9, the x, and the -2/3 into an exponential equation? Think about, what does the 9 represent? What does the -2/3 represent? What does the x represent? How can we change that log to an exponential? What do you think?
9 to the power of -2/3.
There we go. All right, so the base of the log is essentially the base of your exponential, base and base. We know logs are powers, so this -2/3 answer from the log is a power, and then the argument must be the result. All right, so notice how we can't exactly type in log base 9 of x on our calculator because we have a variable in there, but when we convert it to an exponential, I think we could type in 9 to the -2/3 power on our calculator, right? Maybe give that a shot. What'd you get? 9 to the -2/3. Yeah? 0.231. Okay, let's say you wanted to check your work just to make sure that you've solved it correctly. If we were to plug that 0.231 back in for x, the value of this log should be -2/3. Okay, now since it's a base of 9, we're going to do change of base, either using the common log or the natural log, which either one you're comfortable with. Maybe we'll do natural log. So we would need natural log of the 0.231 because that's the argument we found for the log, and we'll divide that by the natural log of 9, which was the base of that log. And we get -0.6669. Isn't that pretty darn close to -2/3, like we said it should be? Okay, it's a little off because we rounded that number, but notice how it's still pretty close. So let's assume that that's correct because we checked our work. Okay, let's go ahead and try the next one. Notice how this is a log, specifically a natural log, so we have to think about if we were to convert that to an exponential function, what's the base, what's the power, and what's the answer? Let's start with the base. If it's a natural log, what base does it have? Common log was a base of 10. Natural log is a base of, yeah? 2.718. Okay, so you could write 2.718, or you could write e. They mean the same thing. Just like for pi, you could write 3.14, or you could write pi. Okay, so there's our base. What would the power be on either of those? Go ahead, Rebecca, sorry. It would be 3, okay, and then it would equal the argument, which was x. Okay, so on our calculator, we could not type in the natural log of x, but now that we converted a natural log to an exponential, we could figure out what x is. So either type in 2.718 to the third or e to the third. Okay, there is an e button on your calculator. Do you see it somewhere? It's kind of small. Do you see how, let me bring it up here. There's the natural log button, but right above it, it has e to the x power. Do you see that? How it's blue? So if you were to hit the second button first and then the natural log button, it'll bring up e to some power. We simply just need to type in 3. Okay, or you could do 2.718 to the third power. In either case, we should get roughly the same amount, which looks like 20.086. right, maybe you want to check your work. So on your calculator, now that we figured out what the value of x was, we can plug that back in for the x and simply type in natural log of 20.086, and it should be something really close to 3. Notice how it is. Okay, so what's nice about these is you can always check your work, make sure you're kind of on the right track. All right, let's try one that looks a little bit more involved. So with that logarithm, let's convert it to an exponential. Can you identify the base, the exponent, and what it should equal? What do you think? Are we starting to see a pattern after a while? Can we write the first initial setup, converting it to an exponential? Let's start with the base. Go ahead, Ashlyn, you want to go do it? 2x plus 1. Perfect. Okay, so let's go ahead and solve for x from there. 3 to the negative third would be 1 over 27, but maybe you feel more comfortable representing that as a decimal. So 0.037 if you want to round. And then we can subtract 1 from that and divide it by 2. So it looks like x would be negative 0.481. Okay. We could double check it if you wanted to, okay? We could plug x back in, type in the log in our calculator, and we should get something close to negative 3. Now the problem is this is a log with a base of 3. You'd have to convert it to a common log or a natural log to check it on your calculator. Maybe we'll try that. Okay, so we would need log of the argument. Now the argument is 2 times x plus 1, so we can type in 2 times the negative 0.481 value that we found, and then plus 1. Close off the parenthesis, and then we'll divide that by log of the base, which was 3. And notice how we get something pretty close to negative 3, not exactly, because since we rounded our x solution, the negative 3 will be slightly off. We're doing okay so far? Solving log equations, converting it to an exponential might be the way to go for us. All right, what if we were to convert this one to an exponential? What do you think, Rebecca?
5 to the x power equals the square root of 125. It'd be like 5 root 5. I think that's like...
Did you type that in your calculator? What do you mean?
Oh, I just wanted to like... I don't know. I like it better if it's all under the radical if you're trying to solve for something. So I converted the 5 to go under the radical itself.
Oh, you did. Okay. If you want to do that, that's fine. Okay. Let's go ahead and try to work out from here. Now, if your x is a power, we're going to have to try to get these bases to be the same. Remember doing that in the exponential unit? That way we can figure out what that power might be. Okay. So notice how 25 is on the left and we're dealing with 5s on the right. We could probably get them both to have a base of 5. How can you rewrite 25 with a base of 5? 5 squared, I heard it. Okay, so 5 squared to the x. Now the right side's a little trickier. how can you rewrite a square root as a power? A square root is the same as a power of, yeah, 1/2. Okay, so maybe instead of a square root there, you want to do 5 to the 1/2 power. Now the first 5 has a power of 1, kind of an understood 1, and the second 5 has a power of 1/2. If you're multiplying the same base together, what do you do with the powers? Think about your exponent properties. You add them. Okay, so 1 plus 1/2 would be 1.5, or as a fraction, 3/2. Okay, looks like we can use another exponent property on the left-hand side. You have a power of 2 being raised to a power of x. How can you combine those? If you have a power to a power. Yeah? You multiply. Good, so that would just be 2x. So now that we have a base of 5 on the left and a base of 5 on the right, we can simply set the powers equal to each other. And let's see, 3/2 divided by 2 would end up being 3/4. All right. Now let's check our answer. Okay, if we were to type in log base 25 of 5 square root of 5, we should get 3/4 as our answer. So on our calculator, since it's a base of 25, we'll have to convert it to a common log or natural log, doesn't matter which one. Maybe we'll do natural log of the argument. Okay, 5 square root of 5 divided by natural log of the base, which was 25. And notice how we get 3/4, or a quarter, or 3/4. So it looks like we used our exponent properties correctly. All right, let's go ahead and try another one. Can we convert that log to an exponential? Let's see, the base would be 2. What would the power be? X plus 2, right. Remember, logs are powers. So whatever the log equals, all of that stuff is a power. And then the answer to this exponential should be 9. So this one's kind of similar to the one we just did because we're trying to figure out the value of x, which is in a power spot, just like x was in the power spot for 25 to the x. How do you want to go about solving for x in this case? Can we get a common base for 2 and 9, like we were able to do with the 5s in the other one? Not quite, right? Because you can only rewrite 9 as a base of 3. So if you cannot get a common base, what's our only other option? What do you want to do, Rebecca? There we go. All right, so let's graph this in y1, and we'll graph that in y2. All right, so y equals, we'll have 2 to the x plus 2 power in y1, and then 9 in y2. Let's see, for our window, let's just do -10 to +10 in every direction, and we'll count by ones. Alright, go ahead and hit graph. So there's the exponential equation, and there's our constant value of 9. We want to try to figure out that intersection point. Do you remember what buttons to press for that? Yeah.
Second power.
Yep. We're going to choose option 5 for intersect. And last step. How do we get the calculator to find it exactly? Yeah, Ashley? Enter 3 times. Good. All right, so the x value looks like 1.17 if we round it. All right, so you could solve that using a graphing capabilities of your calculator. What if we tried to do this one without graphing it? Let's think about this a different way. Do you notice how the logarithm on the left-hand side has both numbers filled in? You know what the base is and you know what the argument is. Couldn't you type this into your calculator and get a value if you did the change of base? For instance, if we did log of, log of 9 divided by log of 2, we'd get 3.17. So essentially the left-hand side is 3.17 and the right side is x plus 2. Doesn't that one seem a little bit easy to solve by hand without using a graph to help you? If we subtract 2, we'll get 1.17 for x, the same answer we got from the calculator. So maybe you have multiple options. You want to graph it to find an intersection. Maybe you can change the base on your calculator to find the value of the log to help you solve by hand. Okay, we got plenty of options. Let's try the next one. Can we convert it to an exponential? It's a natural log, so what's our base? Yeah? E, number E is 2.718. The power would be 5. And the answer to the exponential would be x plus 3. Alright, so on your calculator we can probably figure out e to the 5th. See, that'd be 148.413. And then subtract the 3 over. We'll get 145.413. Maybe you want to check your work, okay? If we were to plug that value back in for x, we would need the natural log of the 145.413 that we found, plus 3, and the moment we hit enter, hopefully it's something really close to 5, which it is. Okay, so one way that we can solve exponent or logarithmic equations is to convert them to an exponential and possibly use our calculator from there to help us out. Okay, we'll eventually talk about other ways we can solve log equations when they get a little bit more intense, but for now this is just kind of an intro. So converting to an exponential is probably the way we're going to go for now. Okay, are we okay with converting? We know what the base is, what the power is, and what the answer is for those exponentials. We hanging in there? Okay, we'll stop there for today. Tomorrow we're going to take a look at properties of logarithms. Just like you have properties for exponents, you have properties for logs. And since logs are exponents, the properties are very, very similar. So if you're very familiar with your exponent properties, these log properties are going to be a breeze. All right, but we'll talk about that tomorrow.